Okay, so thank you for on-site people coming back a little bit earlier before starting the next session. I have a very brief announcement for on-site people. So after finishing this last session today, so we are going to leave this campus to go to the banquet place, and then we prepare the shuttle bus. Therefore, we plan to leave this room around 5:20. It is 10 minutes before we really leave this campus. And then there is a plan about the table, so therefore this one. So please try to find your name in this table. So there are 4 different columns which correspond to different tables in the banquet. We try to make it random so that we can chat with new friends. So therefore, 15 people from the first column, that is a single table. And then let's say 1, 2, 3, 4 from left to right. So please remember your table number. Did you find your name? Please remember. If not, I can also show this on site. And then please try to take a sheet for you. So this is your team. We try to randomize. Color actually the difference of the affiliations, I think, but please don't care about it. It's not very important. Just a number of people here. I'm very sorry, this is confusing. I'm sorry. This number is just a number of people for each table. Different columns, vertical line, corresponds to different table. Okay, please remember. If you don't find it, then please tell us. Okay, that's all from Oliver. Bohan change the third one, number 3. Okay, Bohan.
Okay, Emanuele, sorry for the,
No worries.
you can start sharing.
Can I start sharing? Okay.
Sure. Okay, so we start the final series of talk today. Our speaker is Emanuele Sobacchi from Hebrew University of Jerusalem. The floor is yours.
Okay. Okay, thank you for giving me the opportunity to present. And today I will talk about nonlinear propagation effects in fast radio bursts. So first of all, okay. So first of all, let me briefly summarize the main properties of the propagation of electromagnetic waves in plasmas. And here I will focus on wave frequencies much larger than the Larmor frequency. So, as everybody knows here, the propagation is studied using the Maxwell's equation that describes the evolution of the electric field E and the magnetic field B of the electromagnetic wave. And this equation needs to be coupled with the equation describing the response of the electrons in the plasma that can be used to calculate the electric current. So the electric current is calculated from the equation of motion of the electron in the electromagnetic field of the wave. And here the assumption, the usual assumption is neglecting the Lorentz force. So it is assumed that the Lorentz force is much smaller than the electric force. And since the electric and the magnetic field of the wave are of the same order, of course, this assumption is equivalent of assuming that the velocity of oscillation of the electron in the field of the wave is much smaller than the speed of light. If this approximation is made, the problem becomes a linear problem. One can seek a solution in the form of plane waves. One finds the usual dispersion relation, omega square equals c square k square plus omega plasma square. And this dispersion relation, of course, is responsible for the dispersion that is seen in the dynamic spectra of all the fast radio bursts that we see. So why nonlinear propagation effects? One can estimate the velocity with which the electron oscillates in the electromagnetic field of the wave. And this, the ratio of the electron velocity to the speed of light is usually defined as the strength parameter of the wave A naught. For the typical frequency luminosity of the FRBs, one finds that this strength parameter becomes of order unity at a distance of 10 to 14 centimeters from the engine. This means that close to the engine, so let's say closer than 10 to 14 centimeters, the approximation that the velocity is much smaller than the speed of light breaks down. And in this case, nonlinear propagation effects become important. One cannot anymore neglect the effect of the Lorentz force. So I would like to mention that these nonlinear propagation effects have been widely studied in laser plasma interaction. And for astrophysical applications, there are, I think, two important differences. The first difference is the plasma composition. So astrophysical plasmas could be loaded with pairs and could have strong magnetic fields. And the second difference is that it turns out for the astrophysical applications that even quite weak nonlinear effects, say strength parameter of the order of 10 to minus 4, so distances of the order of 10 to 17, 10 to 18 centimeters from the source are important. So let me briefly outline the topics that I will be talking about. So I will focus on the propagation of the FRB from distances of 10 to 14 to 10 to 17 centimeters from the source. Here I will assume that the source is a magnetar, so I will consider the propagation in the electron-positron magnetar wind at distances, say, of 10 to 14, 10 to 15 centimeters from the engine. And then I will talk about nonlinear propagation effect in electron-ion plasma that could be present at larger distances from the source, say 10 to 17 centimeters. So I will focus on this range of radii and these two different environments. So what happens in the electron-positron wind at a distance of 10 to 14 centimeters? It turns out that there is a dominant instability, which is called filamentation instability, and I will discuss it in the next couple of slides. So the evolution of the FRB, of the vector potential, can be described by a nonlinear wave equation, which is this equation, and there are two nonlinear terms here. One term, the ratio of the number density to the average number density, is due to the fact that the number density of the electron in the plasma is not uniform due to the ponderomotive force. The ponderomotive force is a force that appears when there is a large-scale gradient. Large scale means compared to the wavelength of the wave. When there is a large-scale wavelength gradient of the wave intensity, electrons tend to be pushed out of the regions where the radiation intensity is larger. So electrons tend to be removed from places where radiation intensity is larger due to ponderomotive force. The second nonlinear effect in the wave equation is due to the relativistic corrections to the effective mass of the electrons, which is this term. It turns out that in electron-positron plasmas, the dominant effect is the effect of the ponderomotive force, and the instability develops as follows. So one can imagine to perturb the intensity of the wave in the direction transverse to the direction of propagation. Then the ponderomotive force is pushing electrons outside the regions of enhanced radiation intensity, so electrons tend to be accumulated here, electrons and positrons. In the regions of enhanced radiation intensity, the refractive index of the plasma is increasing, and this is creating a converging lens that is enhancing the radiation intensity even further in these regions. So this creates a converging loop, that a feedback loop that determines the filamentation instability. So one may, of course, ask when this instability saturates. And the top left panel here shows a model of the saturation of the instability that we developed. Dashed line shows the electron number density. The solid line shows the radiation intensity, and this plot is transverse to the direction of the propagation of the wave. So plasma tend to be accumulated into thin sheets, periodically spaced, and plasma is evacuated from the regions in between the sheets where the radiation intensity is larger. So the physics of the saturation is that the pressure gradients that would make these sheets, these plasma sheets, and that would enlarge this sheet, that would broaden these sheets, is balanced by the ponderomotive force. So this is how the instability saturates. And this is confirmed by some particle in cell simulations that we developed recently. So here you see the number density of the electrons in the plasma, and you can see that plasma are confined and there is vacuum in between the plasma density sheets. And the wave intensity, so the wave in the bottom panel, so the wave is propagating in the vacuum region in between the density sheets. So this filamentation instability has two important effects. The first effect is that the wave is propagating practically in vacuum, so scattering processes such as induced quantum scattering are strongly suppressed. The second effect is that the wave is propagating kind of the same as in a waveguide, so the density sheets play the role of the waveguide. So the usual dispersion relation, omega square equals c square k square plus omega plasma square, is not valid. And the dispersion relation is analogous to the dispersion relation of wave propagating in a waveguide. So one could define an effective plasma frequency that is determined by the separation of the density sheets. It turns out that this effective plasma frequency is much larger than the normal plasma frequency, and most importantly, lambda y depends, so the separation of the sheets depends on the burst luminosity. So one would expect large burst-to-burst fluctuations of the dispersion measure in repeating fast radio bursts. And this is observed in this plot. So this plot shows the fluctuations of the dispersion measure as a function of delta t, so the time between two consecutive bursts. And one can see relatively large fluctuations on short time scales. And these nonlinear propagation effects, so the fact that the effective plasma frequency depends on the burst luminosity, could explain this effect. Now let me focus on what happens when the burst propagates a little bit outwards, at distances, say, of 10 to 15 centimeters. So of course the ponderomotive force becomes weaker and weaker, so due to spherical expansion, the ponderomotive force is decreasing at a distance to the -2. At some point, the ponderomotive force becomes too weak, so the radiation filaments cannot be anymore confined by the ponderomotive force, and what happens is exactly the same as what happens in the double slit experiment. So the filaments are diffracted and they interfere with each other. If I may, one can calculate the scattering time of the typical scattering time of the filaments. So due to the interference, one can observe the interference pattern in the spectrum. And typical numbers for these, for the parameters of the problem, is a frequency correlation bandwidth of the order of 100 MHz. And these broadband frequency modulations are often observed in the dynamic spectra of FRBs that are seen here. And finally, let me discuss what happens in an electron-ion plasma at even larger distances from the source, say 10 to 17 centimeters. Evidence for the presence of this plasma comes from Faraday rotation that is observed in FRBs often. So, as before, one can study the evolution of the vector of the FRB vector potential by means of the same nonlinear wave equation. However, the important point here is that the ions are heavy, so it's not very easy to displace the ions. So the number density in this case remains practically uniform. The ponderomotive force is practically ineffective, and the dominant nonlinear effect is the relativistic correction to the electron mass. In this case, it turns out there is another instability. It's called modulation instability. The instability develops because the group velocity of the wave depends on the local intensity. So the wave energy is accumulating in the longitudinal direction, along the direction of propagation. So practically, if I start with a burst of some duration, the burst is broken into several sub-bursts of duration of length lambda z, and this lambda z could be much shorter than the initial duration of the burst. So this modulation instability, of course, could be important for explaining the variability timescale of the bursts. So if I'm a distant observer here, I see a variability timescale that corresponds to the light travel time of these sub-bursts. So the variability timescale that I'm expecting to see is lambda z, the length of this sub-burst created by the modulation instability, divided by the speed of light. And for the parameters of the problem, it turns out that the typical variability timescale could be of the order of 10 microseconds, a few microseconds. Here is an example of very fast variability, which I think could be produced by these nonlinear propagation effects. Of course, the open question which we're working on is how this instability saturates, and we're working on this. So let me briefly summarize as time is running out, let me briefly summarize my talk. So nonlinear propagation effects are important. Nonlinear propagation effects are important close to the source because electrons oscillate with the relativistic velocity in the field of the wave. In electron positron plasma, say at 10 to 14 or 10 to 15 centimeters from the source, there is filamentation instability. The dispersion relation is strongly modified as in a waveguide, and this could explain rapid fluctuations of the dispersion measure in repeating FRBs. As the wave propagates outwards, these radiation filaments are diffracted, they interfere with each other, and this could explain broadband frequency modulation. And finally, at larger distances, in electron-ion plasma 10 to 17 centimeters from the source, there is modulation instability. So the wave intensity is modulated along the direction of propagation, and this could explain the fast temporal variability of the bursts. And this concludes my talk. Thank you, and I'm happy to take questions.
Okay, thank you, Emanuele, for nice talk. So we have a question from the on-site participant. So, Kunihito, please.
Well, thank you very much for a nice talk. So I have a question about the filamentation instability, and you explained the dispersion relation concerning some lambda. So is this a two-dimensional distribution or three-dimensional distribution? So filamentation.
So yeah, let me share the screen once again. So you're referring to this slide.
Yes.
So these simulations are 2D simulations.
Yes.
Turns out that the dynamics of the problem is essentially 2D, I think, because I didn't say, but in the magnetar wind you expect a very strong magnetic field transverse to the direction of propagation. So here it's in the y direction. So electrons could move easily along the direction of the magnetic field, but it's very difficult to displace the electrons in the perpendicular direction. So I would expect like this picture to be true if I'm looking in a plane parallel to the in the plane of the weak magnetic field. So when there is a strong magnetic field, the problem I think is essentially two-dimensional.
Also, you consider some magnetic field?
Yeah. So if let's say if there is in the analytical model we had the magnetic field, and it turns out that these structures are formed. I mean, these sheets are the density sheets are perpendicular to the direction of the local magnetic field. So the problem is essentially 2D.
Sorry, maybe.
I mean, the direction, the out of plane direction is not very important if the magnetic field is strong.
Okay, thank you.
Thank you, Emanuele. Maybe we have another question, but we can leave it for a discussion time. If you possible, please remain. Thank you so much. Let's thank again to the speaker.